And then let's get to today's stuff. So what I want to talk about is, in the previous lesson, we started talking about something called the cast diagram. And I would love somebody in the class to put in the chat or to unmute yourself and tell me, what does the cast diagram or the word cast have to do with the Cartesian plane? And I've left the trig graphs up on the left-hand side, maybe just to remind you, but I'd love to know what you remember from last week. So let's go to Umta. Umta, what do you remember?
Hi, sir.
Hey, Umta.
I think it's like I forgot, but in the first quadrant, it's all trigonomic ratios are positive, and then the second one it's sine, the third one it is tan, and then the last one is cos. That's why it's called a cos diagram, if I'm not mistaken.
Yeah, so the cast diagram tells us where trig ratios are positive or negative. And we talk about something called quadrant 1 being over here, quadrant 2 being here, quadrant 3 being here, and quadrant 4 being here. And so you'll often see me say that cos is positive in quadrant 4 and quadrant 1, because A stands for all the trig ratios. And then I might say something like cos is negative in quadrant 2, because only sine is positive in quadrant 2. So this is just a quick way of knowing whether or not a particular trig ratio's angle is positive or negative. So I want to give you a quick little warm-up test for this. If I said to you the sine of 220, would that be positive or negative just using the diagram, the cast diagram in front of you? And I want you to put that in the chat. Is the sine of 220 positive or negative? Okay, there's a couple of differences. Okay, so the majority seems to suggest negative, which I agree with. But there are some positives. So let me just talk about how we might interpret sine of 220. Now, one of the things that we need to get used to is, when we started trigonometry in grade 10, we only had trigonometry in triangles, essentially, and it's still only in triangles. But this is quite a confusing idea that you can have 220 as an angle. And so what the Cartesian plane helps us to do is understand what 220 degrees looks like. So if you imagine an arm, a terminal arm, kind of rotating around from here, then that angle up to there would be 90. Now, if that angle went to here, that angle would be 180. And if I kept going another 40 degrees, then that would be the angle of 220. When we use the cast diagram, we start here as 0. This is 90. This is 180. This is 270. And if I go the whole way around, I get all the way up to 360. Now, because the sine of 220 is in quadrant 3, only tan is positive here, which means the sine of 220 should be negative. Okay. Give me a thumbs up if you understand why the sine of 220 should be negative based on this drawing. Give me a thumbs down if you don't understand. Okay. All right. Well, let's try another idea. Let's test this idea out again. If I said to you, what is the cos of 320? Is the cos of 320 degrees positive or negative based on this summary drawing? Okay, so I'm looking at the chat stream and I'm seeing lots of positives. And I think what you're realizing is in order to have an angle of 320, if I start here and I imagine going to 90 and then to 180 and then to 270, and then I have to keep going. Oh, excuse my dodgy angle. Let me try again. So, well, it's still pretty dodgy, but you get the idea. So you can imagine this is a radial arm. You can imagine that that angle is 320. Now, just to point something else out is that whenever we evaluate a trig ratio, we do need to have a triangle. And so the triangle that 320 would form would be actually formed like this. But I'll get to that at a later stage in the lesson. But I just want to show you the connection between 320, the angle, and the fact that it forms a triangle. So in quadrant 4, cos is positive, so this would be positive. Okay, that's good news. Let's try one more. What about the cos of 460? What about the cos of 460? Is that going to be positive or negative based on this cast diagram? Now be careful. What does 460 mean? I know that's a bit weird. Like, how can you have an input angle of 460? Has the teacher lost his marbles? Okay, I like it. I see in the chat there's some debate going on. There's a positive, there's a negative, which is good. It means I'm reached your, to use a fancy term, zone of proximal development, right? The edge of your understanding. This is good. So let's explore this. If I have 460, I surely need to go the whole way around, and I'm at 360. Now, how much have I got left to eat up? I now need to go, so 360, another 90 would get me to 450, and then a little bit across here. And so basically my angle will end up in this quadrant. So the angle is to go the whole way around and then a little bit extra. If I was constructing a triangle, the triangle I construct would be like this. But can you tell me, is cos 460 going to be positive or negative? Which quadrant is it in? It's in quadrant number 2, and cos in quadrant number 2 is going to be negative. Yes. Fantastic. Again, give me a thumbs up if you feel like you understand how the cast diagram helps us understand where a trig ratio with a particular angle is positive and where it's negative. Okay, fantastic. Now, here is the second part that we need to know about. One of the things that the cast diagram does is it helps us also reduce angles to smaller values. So if you imagine a triangle that is in quadrant number 1 would look like this. Now, depending on how steep I make this line, it's going to be how big that my reference angle is. But so for example, that would be maybe like 30 or 40 degrees. But if I had like an angle like this, then the angle would be greater. However, what's also going to happen is that I am going to get angles that are bigger than 90 that leave quadrant 1. And so I need to know a way of reducing trig ratios that have big angles to equivalent smaller angles. And so in order to do that, I'm going to teach you something here. So everything in quadrant 1 is going to have the form theta. Everything in quadrant 2, the angle that I get is going to have the form 180 minus theta. Now, this is going to seem weird at first. I just want you to trust me for now. Everything in quadrant 3 is going to have the form 180 plus theta. And everything in quadrant 4 is going to have the form 360 minus theta. Again, still very weird. At the moment, we're just taking this on faith that the math teacher knows what he's doing. So if I say to you, I want you to rewrite the sine of 150. Well, first of all, actually, let me ask you this. I want to ask you, what quadrant is the sine of 150 in? It's in the second quadrant. Okay. In the second quadrant, is sine positive or negative? Okay, it's positive. Okay, so what I'm going to do is I'm going to put a big plus sign, okay, because I want to remember that it must always be positive. Now what I'm going to do is I'm going to use this reduction formula to write this in terms of this format. And so what that will look like is the sine of 150 can also be written as the sine of 180 minus 30. Now, again, I don't think that is too tricky by itself. It's tricky because it's written in terms of this reduction formula, but I think you would give me a thumbs up if you agree 180 minus 30 is the same as 150. So if you agree that this is the same as this, give me a thumbs up. Okay. Now, if you look at what this formula does, let's just practice this for a little bit. So I said the sine of, I'll show you why this is true in a moment, but you're all happy with that. Now I want you to write for me, let's say the sine of 120 using the same idea. So I just want you to rewrite the sine of 120 using these angle structures that I'm just telling you to take on faith for now. So I want you to rewrite it for yourself and then pop it in the chat. So what would the sine of 120 look like? And also, let's say, what would the sine of 240 look like? Actually, let me just go sine of 120 for now. Let's just stay with that. Let's just do the sine of 120. So I'm actually going to leave the plus signs out for now. All I'm going to do is I'm going to say this is the same as the sine of 180 minus 60. And this is what we call using the reduction formula. Now, we're almost there. Let me show you the final step is going to be reducing this. So the sine of 120 is equal to the sine of 180 minus 60. If I want to reduce this, the final step is going to be to say, in quadrant 2, is sine positive or negative? It's positive. And the sine of 180 minus 60, I just write down the number for theta, which is here. So this is going to be plus the sine of 60. I want you to check that on your calculator. Check that the sine of 120 is indeed the same as the sine of 60. And if it's true, give me a smiley face. If it's not true, give me an unhappy face. We do have to indicate positive signs, but I'll show you in a moment. Okay. So this is what we call a reduction. The sine of 120 can be reduced to the same as the sine of 60. Now, how is it possible that this happens? Let's have a quick look at the drawing. If you imagine the sine of 120, the angle is going to be up to here. Okay. Now, if that's 120 degrees, how do we actually get a value for the sine of 120? And the way we do it is we draw a right angle triangle using that angle in quadrant 2. Now I want to ask you, what is the value of the green dot based on what you see on the screen? So if you look at the screen, if I give you 120, the sine of 120, I get 120 gets me into quadrant 2. What is the value of the green dot? Okay, the green dot is 60 degrees. And so we know that the sine of 120 actually gives me the same triangle as the sine of 60. Because it looks exactly, you can imagine that if it was in this quadrant over here, the 120 gives me a reference angle of 60. Then the other thing I need to know is that in quadrant 2 is sine positive or negative, and it is going to be positive. So let's do another example and I'll show you. So my hope was I was trying to show you why the sine of 120 has the same value as the sine of 60, because the triangle for the sine of 120 has to have a 60 in it. Let's try another one to make this idea even more interesting. Well, not more interesting, more clear. If I want to reduce the sine of 240, I'm first going to rewrite it without a plus or minus sign. I want you all to rewrite it in the form that you think it should take. And put it in the chat. How should I write it? It's going to be the sine, if it's in sine of 240 is in which quadrant? It's in quadrant number 3. So it has to have this format. So I'm going to write it as the sine of 180 plus 60. So whenever you are reducing a trigonometric ratio, you first ask yourself, in that quadrant, how do I rewrite the angle? Now, let me kind of show you where it comes from. Bring it back for a second. So the next step is to ask you, if I had to ask you, is the sine of 240 positive or negative? In quadrant 3, it's going to be negative. And using the reduction formula idea, when you use it, all you need to do is theta is going to be the angle that's left behind. And so you find that it becomes minus sine 60. So I still understand that a lot of you will be feeling confused, and that's fine. I'm going to keep going over this idea, but I just want to show you what 240 looks like. If I had 180, 180 would get me to here. Then if I went 60 degrees further, I would get, that would be 240 degrees. However, I don't have a triangle that gives me a way to evaluate what that is unless I form it. So I form it in this quadrant here. If this whole thing is 240, how big is this angle over here going to be? What is the blue dot going to be? So you can imagine that it goes 180 to get there, and then it goes a bit extra to go the blue dot. The blue dot is going to be 60. Yes. Now, the problem is, and the reason we have a negative sign is that in quadrant 3, sine is negative. So tan is positive, but sine is negative. That's why I have this negative in front here. So I get negative sine 60. Now, if your math teacher is telling you the truth, put the sine of 240 in your calculator and see what you get. Put minus sine 60 in your calculator and see if you get the same thing. It must give you the same value. And if it gives you the same value, I want you to put a happy face in the chat. Aha. See a couple of happy faces. Okay, so I'm telling you the truth. This is good news. So let's go and practice this a little bit before our break. So if I said to you, I want to reduce the sine of 163, what I would say is I rewrite it as the sine of 180 minus 17. Now, that is the same value. It's still the sine of 163. If I draw myself a little cost diagram, I realize that I'm in quadrant number 2. That means that when I reduce this trig expression, it's going to end up being positive because sine is positive in quadrant 2. Then what I say to myself is, what is the angle in the triangle going to be? And you don't even have to worry about the triangle too much. You can just focus on the bit that's left up over here, theta. And so I'm going to write this as sine of 17. So it turns out that the sine of 163 is the same as the sine of 17. I want everyone to try and do these next two ones for me. So I want you to reduce the cos of 327 and the tan of 248 to trig ratios with acute angles, angles that are less than 90. And I want you to give that a go now. Now, if you're feeling stuck, then please do put your hand up and I will assist. But I think I probably talked a bit much. And so it's time for you to practice a bit. So question 2 and 3, and then once you've got your answer, you can pop it in the chat. And for those who need a bit of extra, quadrant 1 is this. Quadrant 2 is this. Quadrant 3 is, angles have that form in quadrant 4. Aha. So Kitzel, where does the 17 come from? So Kitzel, I need to write 163 in the form of quadrant 2. And quadrant 2 has the angles, have the form 180 minus something. Now that something in this case has to be 17 because 180 minus 17 gives me the 163. I can't change the value. I'm keeping the value the same. So, for example, in quadrant 2, I don't have the format 180 minus. I actually have the format, it shouldn't be sine, it should be cos, apologies. So cos 360 minus something. Now, what is that 360 minus something going to be? Well, what 360 minus what gives you 327? It's going to be 33. But we still need to make a decision about reducing this. So I'll leave that to you guys and I'll wait for a bit more time. What do we think about number 2 and number 3? And in fact, we can do number 4 as well. Let's do number 4 and then we'll take a break after that one. Would anybody like to come on and explain what they did? Take me through the process for number 2 or number 3. Yeah, let's go to Umta. What do you think?
So sir, I don't know if my answers are right.
That's fine. Give it a go.
But for number 2, I think it was 360 minus 33.
Yep, I agree with you on that. And what's your reduction?
A plus cos 33 degrees.
Okay, how did you know it was plus for cos? How did you know that? You're
because
right.
It was in the 4th quadrant, sir.
Yes, it was in this quadrant over here, and cos is positive. So then all you do is write positive, and then you write the cos of 33. So the theta is just this little bit over here. Awesome. Thank you, Umta. Would anybody like to do number 3 or number 4? Let's go to relay. Hey, how's it going? Can you hear me? Okay.
Hi, sir.
Hey. What was your first step in number 3?
In number 3, I went to the third quadrant.
Perfect.
And,
I agree.
And my answer was tan 180 plus 68 is equals to tan 68. Because of the third quadrant, tan is positive.
Love it. Absolutely agree. So third quadrant has the form 180 plus something. The plus something is really the reference angle or the angle in the triangle, which I'll explain later. But for now, we just know positive tan 68. Awesome. Let's do number 4. Who would like to try and do number 4? Let's go to Mbali and Zanele. How would you do number 4?
Hello, sir.
Yeah.
So 213 is found in quadrant 3. So cos is negative in quadrant 3. So it's negative cos, and 180 plus 33 will give you 218. So we're gonna say cos 13, negative cos 33.
Perfect. Thank you so much. That was awesome. So what I want to point out is it's much easier if you break it out into 2 processes. So step 1, there's no positives or negatives. It's just getting the format right. So I rewrote it where there's a 180 plus or a 180 minus or a 360 minus. So that's step 1. Step 2 is when I decide, is it positive or negative? And I just grab out the reference angle or and so I just want to encourage you to do it as a 2-step process. Now, Shirinj is asking, why don't we use 270 minus? So Shirinj, we are using what's called the standard reduction of the horizontal to start with. We will talk about co-ratios in the next lesson, but for today, I just want to really get a solid understanding of using the horizontal for reduction formula. So Tembi, yes, whenever you're using, well, okay, do we always? There are some situations where we use 270 and 90, but I would say 80% of the time, we're going to use the horizontal lines, 180 and 360. And so for now, for today, I'm just going to ask you to focus on just what we're doing, and then we'll build your understanding every week. If we try and do too much at once, it's like information overload. Okay, now, I'm very chuffed with all your hard work in the first part of this lesson, but I know that it's time for a break. And so what I want you to do is I want you, oh, sorry, that is the thing that I forgot to move out of the way. Let me just bring that down and zoom in. And I want everybody to stand up, and I want you to join me in being a bit active for a second. So, everyone, turn your cameras on and stand up away from your desks. Your brain needs a break. I know you don't want to, but you're gonna have to. Okay, and I want to see some friendly faces out there.
Please turn your cameras on, guys. Let's see your lovely faces.
Okay, so what are we gonna do just to tell our brains that they have a bit of a break? Let us start with a small circles with our hands, and then slightly bigger circles, and then some nice rotations to do this. So just free your arms, and then just swing your arms like this. Part 2 is to swing it. Swing your arms like this. And then part 3 is to stretch your neck out. So just 5 seconds. And the other way. Okay, now let's roll our shoulders back. And let's roll our shoulders forward. And then now let's do sort of that slow turn. So a little bit at first. And then as our bodies get looser, you'll find that you can turn more. And then hopefully by the end, you're twisting quite substantially. Okay, now let us do something high heart rate. So get your preferences in the chat. Otherwise, I'll make a call. But if there's a high heart rate exercise that you want to suggest, today is your day to shine. Any suggestions? Otherwise, I'm going to make the decision, and that's a risky bet.
It says no suggestions.
Okay, we'll do five squats, and then we're going to do another one after that. So 1, 2, 3, 4, 5. Okay, that's part 1. Then it's knee taps. So how does that go again? 1, it's like this. Well, you can't even see my knees because the camera's here. So 1, 2, 3, but we're going to do it by running. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 more. 1, 2, 3, 4, 5, 6, 7, 8, 9. Come on. 10. There we go.
Yay, give yourselves a pat
Tell me you
on
don't
the
feel
back, guys.
better now. Tell me you don't feel better. I challenge you to tell me you don't feel better now. And then here is the brain break question for today. Divide 20 by a half and add 30. What do you get? So divide 20 by half and add 30. What do you get?
That really did get my heart rate up.
I know you feel it every time you do it. You're like, oh, I don't want to do this. And then the moment you do it, it's like, you're like, yeah, my body's, I'm a human.
Yes. Get a little boost.
As a teacher, you need to lean into the cheesiness. Unfortunately, it's just one of the occupational things. Yeah. Okay, what are my answers coming through here? So we have 70 as it seems to be. Let's see if I agree. So 20 divided by a half and add 30. So what I was hoping to trick some of you with is dividing by a half is the same as timesing by 2/1. But it doesn't seem like I caught many of you today. So 40 plus 30, which is indeed 70. So I'll have to bring the thunder next time. But for today, students 1, me 0.
Yay, well done, guys.
Okay, so let's go back to the last bit of this lesson. And we were doing this thing called the reduction formula. So what I want to show you is that if we talk about, let me just talk a little bit about X, Y, and R, and then I'll come back to the reductions process. So when we do trig in grade 10, we tend to think about SOHCAHTOA and this right angle triangle stuff. But what happens is in grade 11, we switch our way of dealing with triangles to handle angles that are greater than 90. So for example, I showed you an angle like the 150, and then 150 gives you an angle that goes into this quadrant. But what we then need to think about is how do we describe the sides and the triangles that we deal with in grade 11 trigonometry, when all of a sudden you can have angles like 220 or 350. We need a way of describing it, and SOHCAHTOA maybe doesn't work quite as well. So what we're going to do is we're going to think about X, Y, and R as being the letters that kind of define how this works. So if you imagine in grade 10, we would have called this H, we would have called this O, and we would have called that A. But because we are on the Cartesian plane, in order to handle triangles in different quadrants, we instead use the Cartesian plane system with X, Y. So basically, if here's your coordinate, you have X across and Y up. And then the hypotenuse is like a radius that's swinging around the Cartesian plane. We call it the terminal arm. So just to show you kind of why this works like it does, here is quadrant number 2. And in quadrant number 2, you will find that your generating angle is 180 minus theta, but the angle that inside your triangle will actually just be theta. And that's why when we use the reduction formula, we can just grab that small little piece out of it when we reduce it, because the triangle is actually being formed not by the full angle, but just by the little bit over here. The other thing I want to point out is that if this is O and this is H and this was A, can you see that the sine of 180 minus theta, or the sine in that angle, in that quadrant, is going to be just Y over R, or O over H? Give me a thumbs up if you understand the sine of 180 minus theta being Y over R. I'm just trying to connect the X, Y, and R definition to this idea. So if you imagine the sine of an angle is, okay, so I've kind of, all right, I'm losing some of you there. Don't worry. Maybe this is a little bit at this stage. I just wanted to show you that in quadrant 2, kind of why we can just grab that little angle out. Okay, I see you loud and clear. I can see a lot of students are finding this a little bit tough. So I'll come back to it in the next lesson. But let me just give you have a look. If you look at quadrant number 3, can you see that the angle that we have in quadrant 3 is going to be 180 plus theta, where theta is just this little bit over here. And then in quadrant 4, you can imagine that the triangle that we get is going to be 360, which is the whole way around, and then back a little bit, which gives me this theta over here. Now, I'll come back to that in the next lesson, but I just wanted to give you some exposure to the X, Y, and R definition that we start to use in grade 11, but we can come back to it. So let's go and practice a different type of question. So I want to ask you the following question. Which acute angle has the same tangent as 220? Which acute angle has the same tangent? What they're saying is, which angle has tan of 220 equals the tan of what? And I want you to vote with either A, B, C, or D. So we're trying to figure out what this thing is. So if we think of the tan of 220, we know that it can be rewritten as the tan of 180 plus 40, because it's in quadrant number 3. And what's more, in quadrant number 3, tan is positive. So we get plus tan 40. And so the correct answer would be A. Give me a thumbs up if that made sense to you. Give me a thumbs down if that didn't make sense to you. Okay. Cool. Let's give this another go, a different type of question. Let's do this one. I'll rub this one out. So this next one is about cos. Express the cos of 110 as the cosine of another angle between 0 and 180. And I want you to use the 4 options to decide which one you think is correct. Which one do you think it is? So I know I have that guideline. I also know I have this. So it's in quadrant 2. So I'm going to take cos of 110 and I'm going to rewrite it as the cos of 180 minus 70. But, so that's step 1. Step 2 says in quadrant 2 is cos positive or negative? It's negative. And then because I'm looking in quadrant 2, if there was a triangle there, I would just have a reference angle of 70. And so I would write it as minus the cos of 70, which is D. So I see some of you got C, and you're not wrong in the sense that there's a 70 involved, but because it is in quadrant number 2, cos is negative in quadrant 2, and so the reduction would be cos of 110 is minus cos of 70. I love what I'm seeing out there. I love it. So should we do one more? Everyone, has everybody got time for one more today? I think we can do one more. Let's do one with a Okay, so here is another type of question, but they even give you a trig graph, which is rather interesting. And I want you to figure out what is the value of cos of 120. Now, this actually is somewhat related to what we're doing, but it's a little bit of an extension to trig graphs. So this is a trig graph. What is the cos of 120 the same as? I'll give you a hint. So 120 is here. So I think a lot of you are looking at this graph and you can see that the cos of 120 would have to be something which is negative. The other way of knowing this is that in quadrant number 2, we know that cos is negative. So there's only one answer which has a negative value, and it's going to be C. And so what I wanted to show you today is, well, let me ask you this question. Can you see how the cast diagram is connected to the trig graph of that function, and how the reduction formula is using that relationship to make things that are equivalent and smaller? So can you see the connection between the cast diagram and the graph? That's what I want to know. That was my goal for this last lesson and this lesson. Fantastic. Okay. So everyone, I think we're going to put what we've learned in the bank. The goal for today was to show you how you can take a trig ratio of a big angle and reduce it to a smaller version, but still have the same value. And I think we made really good progress on that. And so I'm going to end the session there. But Lebo, could you please send a link to the students so they can give us some feedback? And then in the next lesson, we are going to practice further using the reduction formula that we've learned about today. But if you could please give us feedback, that would be awesome. Yes. So Sipo, you can find the past lessons on YouTube, or you can find it on the Watobe website. And they are all, so if you go to the Watobe website, you can click on grade 11, so classes grade 11, then click on trigonometry, and then you will see the recordings. So that's what I would say is a good idea to have a look at. And yeah, we really appreciate your feedback, everyone. So please do leave us some feedback. It's how we know kind of if we're getting the just right pace for the lesson. And it's very helpful to us. Cheers, Faith. It has been fantastic. I hope you have an awesome public holiday tomorrow. Cheers, everyone. Pleasure,
Bye,
man.
guys. Enjoy your
Also-
evening.
Also, oh, welcome to be. So I'm glad you enjoyed it. Pleasure. Yeah, we're untangling the mysteries of trigonometry one reduction at a time. All right, Lebo, if you could just get a screenshot of the poll.